And an engine valve assembly is depicted where J is the inertia caused by the right-hand side of the rocker arm, right? So we have some sort of inertia caused by the rocker arm here. And so we're going to model that as J. And derive an analytical solution for the natural frequency of the rocker arm, right? The assumption is that sine of theta equals theta and cosine of theta equals 1. All right, a little bit of quick engine terminology. This is a rocker arm. So on something like they call them an overhead valve, like an LS engine in a Corvette, or at least the old LS engines, you'd have some sort of push rod and you'd have a cam down here, boop, 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 and it would kind of push the push rod up. By pushing the push rod up, you would push the valve down. This is your valve. It would seat against your engine chamber, and then you'd have a spring, and you'd have some valve seats, valve stems, and seals, and whatnot. And this is how you can move air in and out of your valve. And so this controls the valve on an internal combustion engine, like it's in your car. And so we need to find the natural frequency of it, right? Because it makes sense that we might not want to run an engine around the natural frequency of our components because it will cause our components to resonate and fall apart. So that would be an issue. All right, so let's start this problem like we start every problem. Let's draw a free body diagram. And so I've got the equilibrium state. I've got some sort of pivot here, and I come out, and all of my mass is at the end, because that's what we're only doing, kind of point mass model. And I've got mass and gravity acting down. And now I have some forces acting up. So I have a force that's acting up, which is the stiffness of my spring, K, times how much it deflects, sigma times L, right? Where L here is the length of my shaft, right? And so, and we can do that because we're assuming, I guess let's write that down. We assume that sine of theta is equal to theta. The cosine of theta is equal to 1. So that helps us simplify our equations. All right, so that's my equilibrium state. And now I want my displaced state. So I'm going to have a mass. And it's going to be a little bit confusing, but it's going to be slightly displaced down. And then it's going to be by some amount theta. And again, it's going to pivot around O. Just label that O. And now I have a force acting up from my spring, which is going to be K times delta L, which I had from my equilibrium place, plus whatever I deflected on theta, theta L. And I'm going to have mg acting down. But I also have this damper here that I have to consider, right? And so the damper is going to have a force acting up, and that's going to be C theta dot L. And then I can write my equation for the equilibrium state. It's going to be positive to the left, sum of moments about O is equal to m, not a q, mgl minus kl squared sigma is equal to 0. I'm going to move it to the left just to have a bit more space. And then I get positive to the left sum of moments LO is equal to MGL minus KL squared minus KL squared theta minus CL squared theta dot is equal to our good friend 0. So now I can apply Newton's second law and combining these equations and putting in my J term from the left-hand side, right? So we haven't forgotten about this J here, very important. I get J plus ML squared theta double dot plus CL squared theta dot plus KL squared theta is equal to 0. Now, the standard equation, the standard form of the equation of motion, right? Or this is a term that I have, and I'm going to be honest, it's confusing. I asked you, let's find the natural frequency of this. How do I get the natural frequency, right? It's pretty out there. Like, all of these terms are confusing. Or at least it's just not in the standard that we've been seeing it, right? So that's the power of the standard form, right? If I put this in the standard form, I need to divide by whatever leads my theta squared, right? I don't divide by the mass, I divide by whatever leads, my theta double dot, my acceleration term. And so now I've got theta double dot plus CL squared over J plus ML squared theta dot plus KL squared over J plus ML squared theta is equal to 0. So maybe now if you think about the standard form, I can figure out how to get my equation of motion, because this term here is equal to the square, sorry, that is not true. It is equal to omega n squared, right? And so now omega n is equal to the square root of KL squared over J plus ML squared. And that gets you a nice, in radians per second. And that gets you a nice, clean methodology for getting omega n. You can do the same for omega d, but for getting omega n out of a system, right? Once you have it in standard form, you know what leads the stiffness term is, or what leads the displacement term is just a function of your natural frequency. How cool is that?